In this bifurcation diagram, what are those pink lines called? Phase lines, great. Right, so that's what we talked about last class, phase lines. What do I label the horizontal axis with? Mu. These are phase lines at different values of the parameter mu. Okay. True or false, mu is always an integer? False. False. Mu can take on an infinite number of values. It's a parameter that varies. It's false. Nothing, it's false. It's not always an integer. An integer is a whole number, yeah. It can be a half, right. It says mu is always an integer. Not the case, because mu could be like a half, right? Okay, so last class we did most of the lesson for 1.7. I just want to recap it, finish up that last piece that we didn't get to, and then there's plenty of activities. So, and this is one of the more challenging sections, I think. So you're going to want to take your time and really work through the activities. Okay, so bifurcations are when we're studying a whole family of differential equations, right? So it's not just a single differential equation, but an infinite number of differential equations at once we're studying. Okay, and what makes them a family is that they share some parameter, right? Some parameter which we called mu, but you could call anything. It could be k, it could be L, you know, it could be anything. We typically call it mu when we first start studying it. Okay? So that parameter mu can take on an infinite number of values, and what we're interested in studying is how do the solutions to the many differential equations in the family, how do they look different as you change that parameter mu? And there are certain really special values of mu where all of a sudden the solutions look different. Like, so they might look qualitatively exactly the same most of the time, but there's one value of mu where all of a sudden it looks different. Or maybe there'll be two values of mu where all of a sudden it looks different. So we looked at this example where dy dt was y squared minus 4y plus mu. So again, that's an infinite number of differential equations, one for every possible value of mu. And we said there was one value of mu that made this equation look different all of a sudden. And it was the particular parabola where we were tangent to the x-axis. Okay? And that happened when mu equaled 4. So when mu equaled 4, it was tangent to the x-axis. Everything, all the mu's smaller than 4, we had similar looking solutions, 2 equilibrium points, and it was positive, negative, positive, right? And then all of a sudden at 4, there's only one equilibrium solution, and it's and dy dt is positive on either side. After that, there are no equilibrium solutions. So mu equals 4 is like the boundary, the place where the solutions change, and look qualitatively different. All right, so for every possible mu, we could draw a phase line. Right? So we know how to draw a phase line from 1.6. For every possible mu, we can draw a phase line where we plot the equilibrium points and we state the sign of dy dt with an arrow, either pointing up or down. And then you're definitely going to want to refer to this. I don't have it written, typed out in the notes anywhere, so make sure that you wrote this down somewhere. Okay, this is how to find equilibrium points. Sorry, no, it's how to find bifurcation values. Bifurcation values. So first, set the derivative of the right-hand side of your equation equal to 0. Solve it for y. Then set your right-hand side of your differential equation to 0. Plug in the y value from 1 and solve for the mu. So what's done under there is the example of how you would do it in our example. So in our case, dy dt was y squared minus 4y plus mu. This, the right-hand side of your differential equation, is what I'm calling f sub mu as a function of y. So first take its derivative, set it equal to 0. Then take the whole function itself, set that equal to 0 using the y value from part 1. Solve for mu. Okay, so what we did was we picked two nice numbers on either side of our bifurcation value. We found our bifurcation value was 4. I just picked 5 and 3, easy numbers on either side. And then we can sketch a bifurcation diagram. Okay, so a bifurcation diagram is just a phase line for every possible value of mu, lined up side by side. Okay, so we put mu on the x-axis. The y-axis, sorry, we put mu on the horizontal axis. The vertical axis actually is y. Right. And then for every possible value of mu, we create a phase line, right, where we plot the equilibrium points. We put on the arrows indicating where dy dt is positive and negative. And then you connect your equilibrium points with a nice smooth curve. In the case where the right-hand side of your differential equation was a polynomial, it does turn out that you end up getting a similar looking parabola, because that's a quadratic, right? So you do get like a parabola on its side. Doesn't always, I mean, that happens with polynomials, but you won't always have polynomials. You'll see. There's plenty of examples for you to explore. So this is what we call a bifurcation diagram. So you can see, you can watch the two equilibrium points getting closer and closer together until they sort of merge at the bifurcation value, and then they are no more. Okay, so we did all this part. This is the part we didn't get to before. So I want to use my bifurcation diagram, my phase lines in the bifurcation diagram, to draw solutions, including equilibrium solutions and initial values above, between, and below any equilibrium solutions. So B minus, that was 3, right? We chose that value. It was just a number a little bit less than our bifurcation value. And B plus, that was 5. So this is 3. That's 4, the bifurcation value, and that's 5, a little bit bigger. All right, so when mu is 3, I want to find my equilibrium solutions. I can look at my phase line. I had equilibrium solutions at, like, I don't know, approximately 0.8 and 3.3, something like that. 0.8 and 3.3. So I'm just looking at my phase line. And this should be up, down, up, just like it is for this one. Okay. So I have equilibrium solutions at 0.8 and like 3.2, something like that. So 0.8 is like right here, an equilibrium solution. And a little bit bigger than 3 is another equilibrium solution. So those are equilibrium solutions. And now I can tell from the phase line how to draw the rest of the solution. What if my initial value is right here at 2? What happens when I move to the right? Do I approach the higher equilibrium solution or the lower? How do you know? Because of the arrow on the phase line. So the arrow on the phase line, when I'm between the two equilibrium points, is pointing down. That means my solution is decreasing. So my solution is decreasing here. And it's always decreasing from left to right, so I draw the whole thing decreasing. All right, what if my initial condition is down here, below the lowest equilibrium point? It's going up. Yeah, so here my arrow is pointing up, so it is always going to be increasing. So this goes up towards my equilibrium solution, and this has to be always going down because I have an always increasing function. And I know it doesn't level out because otherwise I'd have another equilibrium solution. All right, and then above, what does it do? It's going up again. So pick any initial condition above there, and it's always increasing. There we go. And I know that I can never cross the equilibrium solutions because the uniqueness theorem. Yep. This differential equation satisfies the uniqueness theorem. So I know I can't ever cross solutions. All right, at 4, I only have one equilibrium solution. And where was that? At 2. Yeah, we can go back and look at our phase line. At 4, I have one equilibrium solution that happens when y equals 2. And then my arrows are pointing up on either side of it. So I'm going to put in my equilibrium solution at 2. And if I start below it, it's increasing. And if I start above it, it's also increasing. Because both arrows are pointing up. And then for 5, I have no equilibrium solutions. Right? Once mu gets bigger than 5, there are no equilibrium solutions, and my arrows are always pointing up. So no matter where I pick as my initial condition, this is just an always increasing function. Something like that. I don't know its exact shape, I just know it's always increasing. Maybe it's just a line, I don't know. All right, yeah, Len. It can't look like e to the x because then that has an asymptote, and that would indicate that there's some kind of equilibrium solution. Yeah. Actually, could it? It might still look like, it might still be able to look like e to the x, because all we know is that it's always increasing. And e to the x is always increasing. Yeah, maybe. I'll have to think about whether or not that asymptote really indicates. It might not mean that necessarily that there's an equilibrium solution. Yeah, maybe, yeah. All right, so your class activities, your first one is like really similar to what we did in the class activities, so you can follow that template, and then they get a little bit more complicated.